Hello, and welcome to a lecture on the stability of two ports. I'm Steve Ellingson. Instability is a property of some two ports which are active, such as amplifiers, and have internal feedback, in which gain becomes variable or unbounded. Stability is the absence of instability. So here's what we're going to talk about in this lecture. First of all, I'll expand on these concepts, stability versus instability. We'll talk about conditions for stability. We'll talk about unconditional versus conditional stability. We'll talk about methods for determining stability. There are at least three that we'll address: sample testing, brute force evaluation, and stability circles, and I'll provide examples of each. And then we'll talk about criteria for unconditional stability. And we basically have two. One is the Rowlett stability factor, and I'll show an example of that. And the other one will be the Edwards-Sinsky stability factor. Okay, so this concept of stability. Let's start with something very, very simple. In this diagram, we have a voltage amplifier. And the gain of this voltage amplifier is A sub V, and it has an input as a function of time x of t and an output as a function of time y of t. So if this is a stable system, what that means is that the ratio of the output voltage to the input voltage over time should be constant and equal to the gain, the voltage gain of the amplifier. So nothing complicated or new about that. It's a very simple idea. Now, you've undoubtedly encountered in a previous course the concept of feedback and how feedback is sometimes used in various electronic circuits. So here I'm showing the exact same thing, a voltage amplifier with a gain A sub V, whose output is now routed through this thing, which has a frequency response H as a function of frequency, and we take the output of that and we add it back to the input. So this is feedback. And again, as you hopefully already know, there are applications of feedback which are good, and there are consequences of feedback which may be bad. However, let's assume that we've properly designed something here. In this case, the magnitude of the voltage output to the magnitude of the voltage input is again a constant with respect to time. However, the gain of this new system may be different, in fact probably is different from the voltage gain. Well, this system is still stable. There's no change in that status. An example of a system which is unstable is a system of the type I showed in the previous slide with feedback, but now the feedback results in a situation where the ratio of the output voltage to the input voltage, which is the gain in some respect, is a function of time. And here's a positive feedback situation in which the gain keeps increasing as a function of time and increasing in an unbounded way. So clearly that is an undesirable situation, at least for amplifiers. Another way a system can be unstable is when its gain, and that's gain in the sense of y of t divided by x of t, varies periodically, and we refer to that as oscillation. So it is possible to have such a thing like this and have the result be that the magnitude of the ratio of the output to the input varies sinusoidally, and that oscillation is also referred to as instability. So I guess in general we can refer to instability as the tendency of a system to be time varying in its overall gain. Now that's a little bit of an informal definition, but the concept is correct. Okay, so our goal for this lecture. Well, let's get back to two-port concepts. So two-port we can describe in terms of its S parameters, and we also know that we can describe the source impedance in terms of a reflection coefficient, the load impedance in terms of a reflection coefficient, and then of course we must specify the reference impedance, Z naught, in order for this all to hang together. So in this context now, can we deduce the stability of an embedded two-port if we know its S parameters and if we know the source and load impedances? So this is the objective of this lecture. So first, a quick reminder, because we'll need this in just a moment, about embedded reflection coefficients. The idea is that, for example, the input embedded reflection coefficient is what we see at the input of the two-port when the output is terminated in some specified impedance. And in that case, we find that the embedded input reflection coefficient is given by this expression. And similarly, we can define an output embedded reflection coefficient, which is what we see at the output when the input is terminated by specified source impedance. So if you're unfamiliar with that idea, please go back to a previous lecture where this is discussed and refamiliarize yourself with this, because this is what we're going to be using going forward. Here are the conditions for stability. This is it, folks. This is the overarching idea. Everything else we do in this lecture will in fact be some interpretation or some manifestation of these equations. What we require for stability is that the magnitude of the embedded input reflection coefficient be less than 1. We require that the magnitude of the output embedded reflection coefficient also be less than 1. Now, we also have another constraint. In order to be sure that we're stable, we also specify that the source and load impedances are such that their associated reflection coefficients are less than 1. In other words, it's too much to ask for any two-port to remain stable if the impedances it sees as its input and output are not themselves apparently stable. So we also have these conditions. Now, unconditional stability. A two-port is said to be unconditionally stable when we achieve stability independently of the source and load impedances, as long as they're satisfying these constraints. So what does this mean? Well, I can make a map of gamma sub L, for example. And that map looks like this. Here's the real part of gamma sub L, and here's the imaginary part of gamma sub L. And all values of gamma sub L for which the magnitude is less than 1 are in this circle. And outside this circle, the magnitude of gamma sub L is greater than 1. And on the circle, the magnitude of gamma sub L is equal to 1. Now, reasonable load impedances, as we've described here, are going to be those for which the value is inside this circle. So what we're really saying is that we end up satisfying these equations for all possible values of gamma sub L which are reasonable, that is, fall within the unit circle. And similarly, we satisfy the equations for all possible values of gamma sub S which fall within the unit circle. Said another way, unconditional stability means that the two-port satisfies the stability criteria, the 4 equations, regardless of the input impedance and regardless of the output impedance. And that's a very desirable thing to have, as we will see as we proceed throughout the course. Unconditional stability is highly prized among RF engineers because it makes things easy. And much of the difficulty in RF design, and in particular in amplifier design, is dealing with conditions in which you do not have unconditional stability. In contrast, we can have conditional stability, which means there are some combinations of the source and load impedance for which those equations are not satisfied. So, for example, it could be that here's our map of gamma L, and maybe we're only satisfying the equations for some region like this, and that there is a subset of those points within the unit circle for which we are unstable, for which we are unable to satisfy the equations. If that's the case, then we say that this is conditionally stable, not unstable or not always unstable, simply that there are some values of source and load impedance for which we achieve stability, and there are some values for which we don't. And this is a very common situation to end up in. Now, furthermore, we'll note here that two ports may be conditionally stable at some frequencies and unconditionally stable at other frequencies. In fact, this is usually the case, and we'll see an example in the next lecture. If you have something which needs to operate over a range of frequencies, which is usually the case, you need to evaluate stability as a function of frequency. So let's talk about methods for determining stability. First, I'll just point out we already know how to do this. So you actually, in fact, already know how to determine stability. But let's talk now about how to practically get this under control. So the first thing is sample testing. Sample testing is just picking values of impedance at the source and the load and seeing what happens, right? So if we know Z sub S and we know Z sub L and we know the S parameters, we can see if we satisfy the equations. If we do, we're stable. If we don't, we're unstable. That's all there is to it. We can do exhaustive brute force testing. And what this means is we do the map. So we do the gamma sub S map, we do the gamma sub L map, and for all values within the unit circle, we check for stability. And this is actually very practical to do in the year 2016 because computers run sufficiently fast that we can systematically check every possible value of source and load impedance because they all fall within the unit circle. So there's a bounded range of values that we need to check. Four-dimensional search, real and imaginary for gamma sub S, real and imaginary for gamma sub L. We can check every one of those four parameters for all possible values that have magnitudes less than 1, and we can completely characterize the stability for all possible values of source and load impedance. And that's what I'm calling brute force testing. We could do stability circles. I'll explain this when the time comes, but it's a faster way or in a somewhat more elegant way to do brute force testing. So we'll talk about that when the time comes. And then finally, in this lecture, we'll talk about the stability metrics. A very important one is known as the Rowlett stability factor. There's another metric, which is known as the Edwards-Sinsky metric, which I'll also briefly mention, and they're both kind of important. So look forward to that.